Welcome to this RocSlope2 webinar on smarter rock slope stability analysis by efficient joint set management and intelligent bolt optimization. RocSlope2 is a one-stop platform for wedge, planar, and toppling failure analysis. And today we'll talk about RocSlope2's two new features, which are multiple joint sets and intelligent bolt optimization. My name is Yalin Dogan, and I'm the product manager for RocSlope2. Today, I'm going to be hosting this webinar session. Okay, let's start with some brief information about Rocscience and our product lineup. We're a world leader in developing 2D and 3D software for civil, mining, and geotechnical engineers. And we're dedicated to delivering industry-leading software, exceptional customer service, and unparalleled technical expertise. From a team of 25 years ago, we've now grown to more than 80 team members across 4 offices, and we're now serving over 10,000 users globally. Okay, a little bit about our software suite. We developed products for geotechnical, mining, and civil engineering. We have 2D and 3D products for slope stability, finite element programs, settlement and pile analysis solutions. We have a web-based borehole logging and data management software, RocSlope. We have products for 2D and 3D rockfall analysis. We also released 2 new programs this year, RSWall, which is a retaining wall stability analysis tool, and RS Seismic, which is a 1D seismic site response analysis software. And we have a number of structurally controlled failure analysis products that deal with joints and discontinuities. We'll be talking about one of those today, which is RocSlope2. All right. Our software ecosystem. We put a lot of effort into the integration between our products. And I'm going to be dealing with the upper right area of this integration map, which has dips and how dips is connected to RocSlope2. I won't be talking about the other integrations today, but they are really a major part of our software ecosystem that they're integrated together, which makes life easier for us engineers. In today's webinar, we'll start with some general information about RocSlope for those who are not quite familiar with the product, and we'll have a quick look at RocSlope's approach to evaluating the stability of rock slopes using 3D kinematic and block-based analysis. We'll then move on to discussing one of the new features we recently included in RocSlope2, multiple joint sets feature. After some technical information on this new feature, I'll show you a live example how you can easily add multiple joint sets into your analysis and import joint sets and joint data from dips. And after that, we'll explore the intelligent support optimization feature, which streamlines the process of identifying efficient and effective support solutions. Finally, we'll wrap up with another practical example on how to optimize support design in our analysis workflow. Throughout the presentation, please also feel free to type your questions in the chat section or the chat box, and I'll try to address most of your questions during the Q&A session at the end of this presentation. And if I won't be able to get them today, don't worry, we'll follow up with an email with all the answers as soon as possible. All right, let's talk a little bit about dips, because the way we picture the workflow for RocSlope2 actually starts in dips, where as usual, you first have a series of joint measurements and run a quick kinematic analysis. When dealing with stability of rock slopes, obviously, structural discontinuities are our major influencing factor for how the slope fails. As an engineer, obviously, we have to look at the characteristics of these discontinuities to determine whether any of them can form blocks for wedge, planar, or toppling type mechanisms that could cause failure on the slope. And obviously, that we don't want any of these failures to impact our local infrastructure, mining operations, or projects as well. So, we briefly talked about dips and how we use it for kinematic analysis. Basically, kinematic analysis is just about looking at the joint orientations and checking for example, in the case of a wedge failure, is that intersection line daylighting on the slope face? And is the dip angle of this line of intersection steeper than the friction angle we put in the program? If the answer is yes, then there's a potential for failure. Now, it's important to remember that this is a pretty simplified check. It's not doing a full limit equilibrium calculation, and there's not much physics behind it. But it's super useful to quickly see how we should expect failures on our slope. Now, if the kinematic analysis suggests a failure, that's where RocSlope2 comes in as the next step. RocSlope2 runs proper limit equilibrium analysis, so it actually creates blocks, looks about the failure modes of these blocks, and lets you factor in all the real-world conditions like external loads, seismic loads or effects, water pressure, and even more advanced shear strength models. So it's basically taking you from that quick, simplified check in dips to a much more detailed and limit equilibrium physics-based look at block stability. Okay, so this is the real vision behind RocSlope2, as I was mentioning before, is to bring wedge, planar, and toppling analysis together with all these new cool features. In the past, with the packages of S-wedge, rock plane, and rock couple, which we have developed over the period of time, you had to run them separately. That means you had to put in your geometry independently. You had to look at each mode of failure independently. And when you should be looking at all the three failure modes at once, determining which one is the most critical one or which is the critical mode, looking at all the factors of safety of these analyses, not having to treat them all independently. Using these three programs independently is also time consuming because you're basically trying to create the models independently. With RocSlope2, it's one model that deals directly with dips, and it brings in your joint data and lets you assess all those failure modes together. And I'll show you an example of that, how that works. Okay, so if you have ever used S-wedge or rock plane before, by default, you put in a deterministic slope, add two joints in S-wedge or one joint in rock plane, and you get a factor of safety. RocSlope2 takes a bit of a different approach. It's really built as an extension of what DIPS does. Instead of just analyzing one or two joints, it starts with what we call a combination analysis. Basically, you put in a list of all the joints that you have on your slope, and the program runs through all the possible combinations. And it will give you all the different modes of failure. What are the critical modes of failure? You can also add basal failure planes, joint sets, all the things you used to be doing in S-wedge, rock plane, and rock topple before. But the real advantage is that you can just bring in your DIPS file directly and run the whole analysis right away. So you'll get an indication of the probability of failure if you're running a probabilistic analysis, for example. What is the critical mode with one set of geometry for the slope? It's doing all of it at once. It's not three independent programs in one, but it's the whole thing together as one working unit. RocSlope2's previous builds already had the capability of performing wedge, planar, and toppling analysis, considering joint orientations from a single joint set or two separate joint sets. With this recent update, now allows RocSlope2 users to define an unlimited number of joint sets, each with independent orientation data and planar and toppling analysis settings. It also allows you to easily import joint sets from a DIPS file, enabling seamless import of joint sets defined in a DIPS file into RocSlope2 as a separate joint set, including their respective joint orientations. We can also selectively include or exclude joint sets from the analysis, which provides flexibility in selecting which joint sets and associated joint orientations to be considered in the analysis. So, this significantly expands joint modeling possibilities and enhances RocSlope2 DIPS integration. Engineers can now selectively include or exclude each joint set from the analysis, which allows more flexibility in allowing or evaluating joint combinations and performing a comprehensive set versus set wedge stability analysis. So, by default, RocSlope2 considers a single joint set when performing block stability analysis. For wedge failure analysis, the software automatically runs a combination analysis, evaluating all possible joint pairs within the set to identify potential wedge-forming combinations. In the case of planar and toppling failures, RocSlope2 considers all joints that fall within the defined sliding lateral limits and toppling lateral limits, which ensures a throughout evaluation of those potential failure mechanisms. So with the new multiple joint sets feature, when we add multiple joint sets to the RocSlope2 model, the block formation logic adapts accordingly. And for the wedge failure analysis, the program evaluates all possible combinations of joints, selecting one joint from each defined set to identify valid wedge-forming blocks. For planar and toppling failure modes, all joints across all defined sets that fall within the relevant sliding and toppling lateral limits are considered. One of the new options we included in RocSlope2 with the new multiple joint set feature is to selectively include or exclude joint sets in the analysis. Including joint sets or using the include joint set in the analysis checkbox now provides full control over which joint sets are considered in the block formation and the stability analysis, of course. So this flexibility makes it possible to isolate the impact of specific structural features. And if you want to perform a targeted set versus set stability analysis, this is also allowed, and customize which discontinuities contribute to the overall block stability results. The new development and the flexibility of being able to add multiple joint sets in the analysis also lets us to enhance the integration between DIPS and RocSlope2. So the improved integration with DIPS now makes it easier to makes it easier than ever to bring in joint sets and orientation data into RocSlope2. During the import process, we can choose to preserve joint sets defined in DIPS, importing each set as a separate editable group within RocSlope2. We can bring in any joint orientation that are not assigned to any set in DIPS into a default group in RocSlope2 as well. So, we can directly import all DIPS joint orientation data into a single predefined joint set chosen from the defined joint set orientation dialog. Okay, great. Now that we've gone through the key features of multiple joint sets feature, we're ready to move on to our live example So we can see RocSlope2 in action. In this example, I'll start by showing you how to run a single joint set analysis. Then we'll expand the model by adding multiple additional joint sets. Then I'll demonstrate how to import joint sets directly from dips. And finally, how to selectively include or exclude specific joint sets from the analysis. Okay, let me bring in my RocSlope2 file. And this is the fresh RocSlope2 model, and this is the screen that you will get once you open up a fresh new RocSlope2 model. A wedge, planar, and toppling block are formed using the default slope geometry and joint orientations used in the program. So let's first check the default project settings, as we have our analysis methods enabled, all of our analysis methods enabled wedge, planar, and toppling. And we have a single set of geometry in the slope geometry dialog. We have the slope face and upper face joint orientations, some geometrical parameters like the slope length or the bench width, and we have our default joint properties defined. The material strength, under the material strength tab, we have the unit weight, and we don't have any water pressure applied in this model for this example. So before going into joint orientations, I would like to first navigate to joint properties to change joint properties and add two new properties to this list. So I'll keep the joint property 1 as default and change the internal friction angle of joint property 2 to 32. And then I'm going to add one more joint property and change the internal friction angle to 38 for this joint property. I will add one more joint property and rename it as toppling joint, and then set its internal friction angle phi angle to 40 degrees. So now I have defined all my joint properties that I'll be using in my joint orientations, or the ones that I will assign to my joint orientations. So let's click OK and go to Joint Orientations tab. So we have joint set 1, or a single joint set defined by default, and we have 4 joint orientations again included in this joint set by default. So let me start with changing the base joint property to toppling joint for the toppling analysis settings. Then I will add 2 more joint sets manually. So to add a joint set, all we need to do is click on Add Joint Set button manually, and a new joint set is defined in our list. Let me change the base joint property again for the second set, and I'm gonna add 2 more joint orientations under this list. So the first joint will remain as default. The second joint in this set will have 45-degree dip and 200 dip direction. And then I'll have 60 degrees dip and 145 degrees dip direction for the third joint that I added under this joint set. Now I'm gonna add another joint set 3, into my analysis, and we can define unlimited number of joints under any of the joint sets. We can define specific planar analysis or toppling analysis settings as desired. And for this joint set, particular joint set 3, I'll have 4 joint orientations. So I'm going to add 3 more. And the first one will have 65 degrees dip and 10 degrees dip direction. Let me quickly define the other 3 joint orientations as well. And then the last one will have 68 degrees dip and 10 degrees dip direction. I'm going to change the base joint property of this joint set for the toppling analysis settings to toppling joint as well. And then let me assign different joint properties to joints under different joint sets. So in order to do that, I'm going to select all the joints under joint set 2 by pressing the shift button on my keyboard. And then I'm going to select assign joint property to all selected joints and assign joint property to. This will assign joint property to shear strength to the selected joint orientations under this set. I will repeat the same step for joint set 3 with joint property 3. So we're all set and ready to move on to our analysis. This is how easy we can add joint sets into our RocSlope2 model. So once I click OK, the program will instantly form or create the blocks, wedge, planar, or toppling blocks based on the joint orientations I have in my joint orientations list. And then calculate the factors of safeties for all the blocks and all the additional information and statistics like block volumes, block weights, and some additional information, statistical information about joints as well. So as we can see, we have 8 kinematically admissible blocks that are formed for wedge analysis by combination of 2 joints from considering 1 joint from each set. So for example, for the first block, this block is specifically formed from joint 1 and joint set 1 and joint 2 from joint set 2. So all the combinations by selecting 1 joint from each joint set is considered for the wedge analysis. And for the planar analysis and toppling analysis, all the joint orientations that we have in the list, they're all considered, and any kinematically admissible joints that can form planar and toppling blocks are they created or formed blocks in RocSlope2 as well. So this is how we basically add joint sets or unlimited joint sets or multiple joint sets into our RocSlope2 analysis. And now let's move on how we can import joint sets from our DIPS file. But first, let us check the DIPS file or the DIPS dataset that we're going to use. And in this DIPS file, we have 283 joint orientations defined with their traverses. We have sets defined, which we will discuss in a bit. And we have some additional features about these joints defined as well, like distance, spacing, length, and type of the discontinuities as well. So let me go to contour view. We can see the poles of all the joint orientations in the grid data. And currently we're looking at the unfiltered data, but let's look at the filtered data based on the discontinuity type. So let's navigate to bedding discontinuity type, and we have 1 joint set for the bedding type discontinuities in our grid data. Let's move on to the shear type filtered joint orientations, and we have 2 sets for shear type joints or discontinuities in our dips file. And if we move on to joint type discontinuities, we have 4 sets defined in our dips file. So that makes a total of 7 joint sets defined in our dips file, as well as we have some unassigned joints which are not part of any joint set in the dips file. So they're not assigned to any joint set in the dips file. So we're going to import this data set into our RocSlope2 model. Let's move on to joint orientations once again and click on import dips and select the dips file that we're going to use. So once I click OK, import from dips dialog pops up, which enable us to import the planes from the grid data, which means all the joint orientations in the grid data will be imported into RocSlope2. Or we can just import the user planes or mean set planes if desired. For this example, I'm going to import all the joint orientations from the grid data. And under the import settings, we have preserve joint sets defined in dips checkbox selected. So once this is enabled, joints will be categorized into joint sets as defined in the imported dips file, or they will be the joint sets will be imported with associated joint orientations from the dips file into RocSlope2. If I deselect this checkbox, RocSlope2 enables me to import these joint orientations from a dips file into single predefined joint set. But I want to import the joint sets from the dips file, so I'm gonna keep this checkbox selected. And we have a couple joint options as well, which basically use to override existing joint sets if we have any predefined joint sets, or we can choose to add these dips joint sets as an additional sets under the list and keep those manually added joint sets as well. But I'm going to override existing joint sets. And then we have the option to import unassigned joints from the dips file, which are not part of any joint sets, as a single group into RocSlope2. So once I click OK, again, instantly the joint sets and any associated joint orientations with this sets are imported into RocSlope2. So we can assign any joint property. Unlimited number of joint properties can be defined and assigned to any joints that we want. We can assign different planar and toppling analysis settings for each joint sets as we want. I'll keep the default settings and click OK to see the analysis results. And the program will compute, again, all the possible kinematically admissible blocks for wedge, planar, and toppling analysis accordingly, and will show us the lowest factor of safety block at all times after rerunning or recomputing the analysis. And in this case, we have these lowest factor of safety blocks, but we can always switch between formed blocks for each analysis type and see additional information about these picked blocks as well. So let's look at the Sternet plot or Sternet as well. And let me disable show intersections and show failures. And we can see all the joint poles similar to dips Sternet plot in RocSlope2. And as you can see, we have different colors for each joint sets, which is basically the color options that's available in the joint orientations dialog. So we can assign like different colors to these joint sets, and they will be reflected in the Sternet plot as well for visualization and quick identification of these joint sets. So let me close the StirNet view and let us see how we can selectively include or exclude joint sets from the analysis. Currently, by default, after the import, all joint sets are included in the analysis because the include joint set in analysis checkbox is selected for each joint set. So let me go and deselect these checkboxes for joint set 5, 6, 7, and unassigned joint set, which basically excludes these joint sets from the analysis. And we will only include joint set 1, 2, 3, and 4 in the analysis. And the program and the algorithm will automatically adapt to it and look for block forming joints only under these included joint sets. So let me click OK. Again, instantly the program will recompute the analysis and we get less number of blocks for wedge and planar analysis, of course, and no blocks formed for toppling analysis if we consider only first 4 joint sets in our analysis. So again, the list of all kinematically admissible blocks, they're formed for wedge and planar analysis, and then factor of safeties and some additional information and statistical parameters are calculated for each block as well. So let's move on to StirNet plot once again. And you can see this StirNet plot is also updated or refreshed based on the included joint sets in the analysis. So any joint sets that are excluded from our analysis, they're not part of the StirNet plot as well. So let me close this StirNet plot and switch back to my DIPS file. I'm going to run a set versus set wedge kinematic analysis in my DIPS file. So let's move on to kinematic analysis. Let's display kinematic analysis as well. Let me select wedge sliding and then move on to set versus set analysis. Joint set 1 versus joint set 4 is selected in this case. So let me click OK, and we find that we have 148 critical intersections that can form wedge blocks when we have a set versus set or targeted set versus set analysis between joint set 1 and joint set 4 in our DIPS file. So let's simulate the same case in RocSlope2. So going back to joint orientations and excluding joint set 2 and 3 from the analysis as well, this led me to only have a set versus set analysis between joint set 1, which is included in the analysis, and joint set 4, which is again included in the analysis. So let me click OK. And under the wedge analysis, and we can see that blue frame indicates that the active analysis window is wedge analysis. We have 148 wedge blocks formed, as in the case with DIPS kinematic analysis. So every kinematically admissible block in our kinematic analysis, they're formed in RocSlope2, and we have proper limit equilibrium physics-based calculations and results as well for these blocks. Okay, so this is how we import joint sets from DIPS, how we can selectively include or exclude joint sets from the analysis, and how we can run a targeted set versus set analysis with this new feature. So going back to my presentation, let's move on to our next new feature, which is the intelligent support optimization. This new feature automates the design of the most effective support configurations, which saves times, minimizes the resources, and improves the safety margins. So support design in rock slope stability analysis, can be one of the most time-consuming parts of the modeling workflow, especially when we're working with thousands of blocks, as in RocSlope2. So RocSlope2's existing bolt pattern tool, which is an advanced feature from the older programs, it already enabled us to define custom bolt properties and layouts, but configuring bolt spacing to meet the safety targets, it often requires repetitive manual adjustments of horizontal spacing and vertical spacing, until the desired factor of safety is achieved or satisfied for all analyzed blocks. So this new feature introduces automation into uh, uh, the support layout design by allowing us to specify a target design factor of safety and automatically generates an optimal bolt spacing configuration that satisfies it across all analyzed blocks. So this, of course, eliminates the need for trial or error and repetitive manual iteration for the support design. So this helps us arrive design-ready solutions more quickly, obviously. So both pattern configuration for intelligent support optimization is built directly into the add bolt pattern dialog. So it maintains a familiar workflow with traditional manual bolt pattern design. So once the use intelligent support optimization checkbox is selected under the bolt pattern configuration, group box RocSlope2 allows us to select either a square or rectangle bolt pattern and additional parameters like horizontal interval, and if the rectangle configuration is selected, horizontal and vertical ratio is also required, and which we're gonna see in a bit in our second example. So for this next example, I'll begin by running an unsupported analysis to establish a baseline. And from there, I'll show you how to intelligently optimize the bolt pattern, then modify the bolt properties, and rerun the optimization to see the changes in the configuration as well. And before we wrap up, finally, we'll re-optimize the bolt spacing for different target factors of safety. So once again, let me move on to my RocSlope2 model, and I'm going to enable or include all joint sets to analysis, which we imported from our DIPS file. So this will be our base model, unsupported base model for using intelligent support optimization feature. So let's move on to support tab. And under bolt properties, let me define a simple bolt for support type with 100 kilonewton force and a passive force application, which this bolt property will be used to design an optimal bolt spacing. So let's click OK and go to Add Bolt Pattern. So under Add Bolt Pattern, we have bolt properties to select from the list. We have the bolt length, the orientation, application orientation of the bolts, which is normal to the selected face by default. We have installation face, which is again slope face by default, and we have bolt pattern configuration group box. If the use intelligent support optimization checkbox is not selected, it's a manual process to change the horizontal and vertical spacing as well as the offset. And if we select this checkbox, now all we need to do is define a bolt pattern configuration which is either square or rectangle. And if the rectangle is selected, we need to specify a horizontal and vertical ratio, which basically controls um, which what will be the spacing or larger on either horizontal or vertical direction. And if we use this ratio as 1, it's basically a square pattern. And let us switch back to square for this example. And horizontal spacing interval controls the interval change or spacing change between each iteration until the program finds an optimal spacing that satisfies the target factor of safety for all analyzed blocks. So I'll keep it default for this case as well. Let me click OK. So the program will recompute and automatically it will identify an optimal bolt spacing that satisfies the target factor of safety, which is default as 1. And this is user changeable as well. And we're going to see this in a bit. But the optimization is done. And we can see the bolt pattern spacing on the status bar at the lower part of our RocSlope2 model, which is 2.5 meters to 2.5 meters square pattern in each direction. So this pattern is the optimal spacing pattern with 0.5 interval as we defined to satisfy target factor of safety for all analyzed blocks. So this can be refined as well. And we can change, for example, the bolt force or the bolt capacities to rerun the analysis, find another optimal spacing pattern for the new set of parameters. So let me change the force of this bolt to 50 kilonewtons and let me rerun the analysis. So since we reduced the capacity or the force of the bolt, I just expect the program to find a finer or less a bolt pattern which has less spacing. So let's see, the calculation is done and we can now see the optimal bolt spacing in this case with the new bolt properties that we use. The new spacing is 2 meters by 2 meters. So this is the optimal spacing to satisfy all to satisfy the target factor of safety for all analyzed blocks with the given configuration. So let's go to Home tab and select Project Settings, and under Analysis, let me change the design factor of safety as well. So by default, as I said, the defined design factor of safety or target factor of safety in RocSlope2 is 1, but I can change this to as well, and let me enter 1.3 in this case. So my new target factor of safety is 1.3 for all analyzed blocks. So clicking OK will recalculate the analysis and reoptimize the bolt configuration. So the general rule here is whenever you add, delete, or modify a parameter, an input parameter, the program will recompute all the blocks and factor of safeties and additional informations for these blocks. And if use intelligent support optimization is selected, it will also reoptimize the bolt spacing. And in this case, since we increased our target factor of safety, and since 2 meters by 2 meters spacing is not sufficient to satisfy 1.3 for all analyzed blocks, the program rerun the computation, the optimization, and then we get a new spacing which is 1.5 meters by 1.5 meters in both directions. So this is our new optimal configuration, support configuration or bolt configuration that satisfies 1.3 target factor of safety. for all the analyzed blocks. This concludes the examples and technical information about these two new features. If you have any questions about the information presented in today's webinar or any general inquiries about RocSlope2, please let me know.